we're going to start exponential functions, growth and decay, section 7.1. So we're starting into chapter 7, which deals with exponential and logarithmic functions. Okay, this is something that does pop up on the ACT. Those of you who took John Baylor, I know would have seen for sure the logarithmic functions. I know some people ask me about them. All right, and we'll see a lot of that here in chapter 7. So exponential functions, growth and decay, section 7.1. First thing we're going to talk about is what does exponential growth and exponential decay mean? The base of an exponential function indicates whether the function shows growth or decay. Okay, so the base shows whether it means growth or decay. Now, what does it mean to say growth? When you think of growth, what do you think of going which way? Up. So growth's going up. When you think of decay, it means going which way do you suppose? Down. Very good. So that's what we're thinking here. All right, here is the model for an exponential function. F of x equals ab to the x power. Recognize the x here is an exponent. A is a constant. Okay, nothing to worry about with A. A can be any number wants to. We're not focused on A. We're going to focus on B. B is what's called the base. Makes sense. B base. Okay. The base is a constant. If B is between 0 and 1, the function shows decay. So what's the number that's between 0 and 1? As a decimal. Anybody has a decimal? 0.5. So if B was, let's say, 0.5, that'd be decay. If B is greater than 1, then the function shows growth. What's the number greater than 1? 2. Okay, so anything greater than 1, it shows growth. Alright, and that's what we're going to talk about today. We're going to be graphing some functions and determining whether it is growth or decay. Yes, sir?
What if it is 1?
What if it is 1? It's a great question. What if B comes out to be exactly 1? Does anybody know what happens to it? Huh? It is a flat line, actually. Why? Because anytime I take 1 to an exponent, what am I always going to get back out? 1. So I'm just going to get whatever my constant out front would be, actually. So, nice question. 0, it would be technically the same thing here because, yeah, it'd be 0 in the end. Good question. Yeah. Good work. So, yeah, it does have between 0 and 1, and it has to be greater than 1. So, let's look at the first one here. First example. F of x equals 1.2 to the x power. Okay, so my b here, my b is always what is raised to the power. My b is 1.2. That is greater than 1, so that's going to represent what is called a growth function. It's going up, exponential growth. Next one, I have 10 times 0.6 to the x power. 0.6 is my base factor, because that is what's associated with the variable. It is between 0 and 1, so that is what is now my decay factor. Okay, or that is what shows exponential decay. So again, we're looking at the number associated with the exponent. If it's greater than 1, growth. Between 0 and 1, it's decay. So let's look at the first couple here. Number 1, tell whether each function shows growth or decay, then graph it. So number 1 here, what is my A term going to be? Remember, A is the constant. What's my constant in this one? It is, anybody? A? 0.8, yep, because that's my constant. My B is my base. The base is what's associated with the variable. What's my base here? Okay. Now my base, that's going to determine whether it's growth or decay. It's 1.6. Does that determine growth or decay? That determines growth. Okay. Now let's do number 2 real fast, and I'll show you how to graph it. So number 2, what's my constant here, Andy? Constant is? What's my base, Maddie? Growth or decay, Maddie? That is decay. Because it's between 0 and 1. Now, good with that. If you have the free graphing calculator app, it is the best app to use when graphing this. So if you don't have it, make sure you download that app, and I'll show you how to graph it there. Okay, so take a couple seconds to download that app. So again, using the free graphing calculator app, you can graph it and then look at it. And this would be a growth graph. It'd be something like that. And then my decay graph will be going down and something like that. Okay, so there's my growth and decay graphs. Again, somebody asked earlier, can I just take a screenshot of my graphs and then send you those? Yeah, go for it. If you have a graphing question, if you just want to take screenshots of your graphs and submit those for your homework, that's fine. That would work. Okay. So let's try number 3 here. Tell whether the function shows growth or decay, then graph. Well, number 3 here, f of x equals 3 times 2.5 to the x power. Would that be growth or decay, Jack? What are you saying?
Growth.
That is growth, because my base is larger than 1, so that is a growth graph. Now again, you could do a table here of values if you really wanted to. Otherwise, you could graph it on your graphing calculator app. Anybody want to take a couple seconds and graph that. So I think we all got the graph now. And again, if you sketch it, it looks something like that right there. Take a couple seconds, try numbers 4 and 5. So as you look at these, numbers 4 and 5, would 4 give me a growth or decay graph, Maddie? That'd be decay. And what about number 5, Phil? Growth or decay? That is a growth graph. So you look at number 4. I was trying to think if I get this correct here. Let's see here. Is it like that for number 4? Is that a pretty good sketch of it? And 5, what's unique about 5? It's upside down. Yeah, if you look at it right there, it'd be something like that. Why is it upside down? Does anybody know why? Because it's negative. That's like a reflection. It's like flipped across. Everything's on the backwards now. Nice job. All right, now why is this important? Well, again, like in math, why is this important? Well, a lot of this goes back to interest, loans, banking. Someday in your life, you probably will have to take out a loan. Some of you, when you graduate here in 2-3 years, you'll be taking out loans for student loans and types of things. Okay, and a lot of times they have interest rates on those, or increase or decreases amounts or something like that, percentages. When initial amount A increases or decreases by a constant rate R over a number of time periods T, this formula shows the final amount that would come out. Okay, so here's our formula, and don't worry, it's not near as confusing as it looks. A of T, the final amount, is a function of the time T. So again, this is what my final amount is going to be. A is the initial amount. What does it mean to be the initial amount? What's another word for initial amount? Starting amount. What I'm going to start with. Okay, initial amount is what I'm going to start with. The rate R is usually a percent, so like 10%, how much I'm increasing or decreasing. And then time T is measured in years. So again, nothing out of the ordinary here that we haven't seen. So initial amount of 15,000 increases by 12% per year. In how many years will the amount reach $25,000? Okay, great question here. So what's my initial amount here? What's my starting amount? I'm starting with 15,000. What is my rate? 12%. Now, anytime I do this, I always want to convert it to a decimal. How do I convert a percent to decimal? Move the decimal 2 places. Nice job. So I substitute those values in. Okay, this is the key right here. So I have my initial amount, and I want to take 1 plus 0.12. Does anybody know why there's a 1 there? Why I'm adding 1 to that rate? Okay, it's because my amount is increasing. So if I think about if I multiply by a percent, let's say I take like 50%. If I do like 50% of 4, does my number go up or down? Down, right? So I want to increase it by 50%. So 100% is the same number. So I'm at it. If I take it times 1, I get the same number. So if I take it times 1.12, now I'm increasing it by that 12%. So that 1 comes because I'm wanting to increase it. All right? So if I'm increasing, I'm adding it from 1. What do you suppose I'm going to do if I decrease? I would subtract from 1. Nice job. Okay, so here I have my function now. F of t equals 15,000 times 1.12 to the t power. So I would go to my graphing calculator now, and I would graph that in. So again, 15,000 times 1.12 to the t power. After you get done graphing that in there, you can look at your graph. Graph won't help you much there just because it's kind of an exponentially large graph. If you go to the T table on your graph, it should be the 3rd or 4th one. Which one is on the bottom there, Andy? The one that says T table? It was the 5th one. So if you go to your T table, which is the 5th one from the left, it will give you all of the X and Y values. There now I can see where is it my y value is $25,000? So I'm looking for the y value of 25,000 because t is my x, time in years. And it says, what do you say, Maddie? It would be between 4 and 5, which actually, if I look at this, my answer said about 4.5, which is a pretty good estimation, I would say. Nice job. Yes, sir.
Do you have to add the t power at the end of it?
All right, so again, yeah, you want to type that into your equation, and then go to t table and look for your values where 25,000 is. And again, it falls between 4 and 5 there, so an estimation of about 4.5 years should be understandable on that one. Okay, let's try number 6 here. Let's first set it up. It says, write an exponential function and graph the function to solve. An initial amount of 40,000 increases by 8% per year. In how many years will the amount reach 60,000? So what is my initial starting amount here, Jack?
40,000.
What is my rate here, Jack?
8%.
Now, what is that as a decimal?
108.
That'd be 0.08. Nice job. Because again, I moved it 2 spots there. So what is my equation going to be here? It's going to be my starting amount, which is what, Jack?
40,000.
So 40,000 times 1 plus my rate gives me 1.08 to the x power. And I would graph that function now. So you'd graph that function into your graphing calculator, hit the t-table, and when you hit the t-table, you want to look for where f of t means my y value here in this instance, where f of t is 60,000. And where does it say f of t is approximately 60,000? Between what 2 numbers? It's between about 5 and 6. If you had to take a good estimate, what would you say? About 5.5, or more this way, or more this way? Which one would you say? About 5.5 years. Nice job. And again, I can sketch that graph if I needed to. I started at 40,000, about 5 to 6 to be up to 60. Do something like that, probably. Nice job. Try number 7 on your own. Take a couple seconds. Try number 7 on your own. So as you look at this, what was the equation you set up, Mark? What was the equation you used?
Y equals 100,000 times 1.04. Right.
To the x power?
Yeah.
Correct. Now when you do that graph, start out there at about 100,000. And I think it's about like right there. I think your graph goes something like that. If it's 2005, predict the year's value will be at least 130,000. Well, where does 130,000 fall between? Which years? Falls between 6 and 7. So what actual years would that fall between? If it's 2005 now, where would it be?
2012.
That'd be 2011 to 2012. Nice job. Again, all that's on that free graphing calculator. Makes it a lot easier. Does everybody agree that makes it a lot easier? Graphing calculators? Yeah. Here's your assignment.